Chapter 10, Section 6 is all about growth and decay, and we talked a little bit about these types of functions in the last section when we were going over exponential functions on the graph and how they look like. And I had talked to you about what a growth function looks like, what a decay function looks like, and we're going to explore these a little bit more now today by looking at equations that we can use to help us find how much something is growing or decaying by. So a lot of times these types of situations will show up when you're talking about like financial situations. So if you've put money into an account, or if you've taken out if you've bought something like a house or a car and it's losing value or it's gaining value. It could be used if you're talking about population of a city, if a city is growing or if people are leaving the city. So those are just some different situations that you might see exponential growth and decay show up. We're going to talk first about exponential growth. So remember, exponential growth means that something is increasing over time. The formula that you're going to use for this is y equals a times, in parentheses, 1 plus r raised to the t power. And you need to know what some of these things mean. So the little a is talking about the initial amount. So this would be how much you invested in, how much you took out, like when you bought, like how much a house was worth, how much a car was worth, those kind of things, like initially. 1 is just going to be there. That's that number that we need to use. Now r is going to be your rate of change, and so that's going to be usually a percentage. So they're going to say that it's increasing by so much percent. When you're dealing with the percents, though, I want you to make yourself a note here. You have to express percents as a decimal before you plug it in. So if they gave you something like 4%, you don't want to put a 4 in for r. You want to put 0.04 in. And I found that by just dividing that percentage by 100, because percentages are usually out of 100% when we're talking about the whole piece. So you want to make sure that you divide that that percent by 100 to get the decimal that you're going to use. Now t represents time. So like how long a situation has been occurring for, how long money has been in an account, how long you've had a car or you've owned a house or something like that. So let's take a look at this example here together before you guys try one on your own. So it says that the prize for a radio station contest begins with a $100 gift card. Once a day, a name is announced. The person has 15 minutes to call, or the prize increases by 2.5% for the next day. So looking at just this information, I should be able to identify some of those key things that we need for our formula. So the initial amount is your A. That would be that $100 gift card that they're starting with. Now time would be a day, like they're doing this every day until somebody calls in and claims the prize. And then R would be your rate. Now it says that it's 2.5%, so we divide that by 100 to get 0.025. So then you can see how they took those numbers that I just kind of found from reading through my problem, and they put it into my equation there. So y equals 100 times that 1 plus 0.025, all of that's raised to that t power, because again, depending on how many days this lasts, you know, if someone calls it on day 1 versus day 2 versus day 3 versus day 4 or whatever, that t could change. And so if you follow up on this second question, it wants to know how much will the gift card be worth if no one wins after 10 days. So if this contest continues to go on for 10 days, how much is the person going to get if they finally call in? So we're going to use that equation, 100 times that 1.025, but instead of a t, we're going to put 10 in because that's how many days it's gone by for. And so at this point, you're going to have to use your calculator to do this. I would probably do the 1.025 and raise that to the 10th power first, and then take that times 100. And so this is going to be worth $128 by the time that that person, or whoever it is, calls in to claim that prize. So for this practice problem, I want you guys to read through it. I want you to identify your 3 things, like what is your initial amount, what is your rate, and how long is this lasting for? Put it into your equation and then try to evaluate it. When you're ready to see the answer, go ahead and keep watching the video. So the initial amount that we put in for tuition is that $10,850, so that's going to be your A. The rate has been rising by 5% every year, so take 5% divided by 100 to get 0.05. And T, we want to figure out how many years have passed here. So it says that it has been rising since 2000, and they want to know what the cost might be for 2015. So from 2000 to 2015, 15 years have passed, so that's going to be your T. So for our equation, you start by using that initial amount, that 10,850. You're going to do 1 plus your rate, 0.05. You're going to raise that to the 15th power. So you can combine that 1.05 first, then raise it to the 15th power, take it times that 10,850. We should have been able to estimate then that college tuition in 2015 was going to be $22,556.37. If you did not get that answer, go back and try again and try to do this, take it piece by piece. You don't have to try to do this all in one big chunk. And if you are trying to do it in one big chunk on your calculator, make sure you're using parentheses so that your calculator is reading the problem the correct way and it's doing the right thing at the right time. Now, another situation that might use exponential growth is something called compound interest. So this has a different equation right here. So capital A is going to be like your answer, just like Y on that last one represented our answer after we did our calculating. So that would be kind of what's the amount that you have after this process has occurred. Capital P represents the principal, or again, the initial amount. So a lot of times when we're talking about compound interest, we're talking about putting money in an investment account and we're letting it sit there for so long. So that would be how much money like you put into the account to start with. Again, you have 1 plus. Now this next piece has changed a little bit. R is still your rate, so still make sure that you guys are representing your percents as decimals. Now, N is talking about the number of times that the interest is compounded each year, and this can change depending on the situation. So some key words to look for when you're talking about N would be annually. Annually would mean like one time, so it happens every year. Semi-annually would mean that it's happening twice a year. Quarterly would mean that it's happening 4 times a year, and monthly would mean that it's happening 12 times a year. So those are just some phrases that you might see within the problem, and that's just telling you how many time periods that they're doing this at. So how many times a year are they compounding your interest? And then T again is time in years. So for how many years did this happen? So if they do like a quarterly compound, that means that every year that the money sat in the account, it was compounded 4 times. And then that money is just building onto itself. So, for example, Maria's parents invested $14,000 at 6% per year, compounded monthly. How much money will there be in the account after 10 years? So, your principal is at $14,000. That's how much they put in initially. R is at 6%, which as a decimal would be 0.06 because you have to divide that by 100. It says that it was compounded monthly. Okay, so N would be 12 because there's 12 months in a year. And they want to know how much will be in the account after 10 years of this happening. So T would be 10. So those are those key things that you're still going to want to be able to pull from your problem so that you can then come here and type it into your equation like they did. So they put that 14,000 times 1 plus your rate divided by your N, so 12, and then that's raised to 12 times 10. Again, because this one's a little bit more complicated than the last one, take this piece by piece. So you can see what they did first is they evaluated the parentheses. They did all of this to get that 1.005, and they took 12 times 10 to get 120 up there. Then they probably raised that 1.005 to the 120th power, took it times that 14,000 to get their final answer here. So $25,471.55 will be in the account after 10 years. And what that means is that $14,000, it just sat there in the account and it was earning interest. They weren't doing anything to the money. They weren't adding anything in or taking anything out. They just kind of let it sit, do its thing, and let it accrue interest over that time period. And that's how much they had at the end. So I want you guys to try to do this example. So read through, identify those things, your principal amount, your rate, how many times did this happen in a year, and how long was the money sitting in that account for, and then go ahead and keep watching to see what the answer should have been. So your grandparents invested $1,000 for your college education, so that's your principal amount. It has an interest rate of 4%, so 4% as a decimal would be 0.04. It was compounded quarterly. Quarterly means that it happened 4 times every year, and it was done for 18 years. We want to figure out how much money you will have for college. So I would have done 1,000, and then in parentheses 1 plus my rate, 0.04, divided by my n, 4, raised to the 4th times 18, that n times t. And so when we do that, we should have gotten $2,047.10. All right, the last thing I want to talk to you guys about is exponential decay. Now this equation is very similar to exponential growth that we saw at the start of the chapter, or the section. The only difference is that instead of 1 plus r, it's 1 minus r, because you're losing stuff over time. So this would be if something's losing money, if something's losing value, if a town's losing population. So instead of having a positive interest or positive rate, it has a negative rate. Everything else about it is the same though. Like A is still your initial amount, R is your rate still as a decimal, T is still your time, so however long that this lasted for. For example, a fully inflated child's raft for a pool is losing 6.6% of its air every day. The raft originally contained 4,500 cubic inches of air. We first want to figure out what is an equation to represent the loss of air here. So I would identify those couple of parts from your equation. So it initially contained 4,500 cubic inches, so that would be your A. Your rate would be that 6.6%, which you divide that by 100, so it would be 0.066. So you can see how they wrote their equation here. They plugged in those pieces, and they simplified it. Now, T would be how many days that we're looking at, or how long that this has been deflating for. So, for example, if they wanted me to figure out what it was after 15 days, or 20 days, or 30 days, I would plug that number in for T. So let's take a look at this practice problem here. The population of Campbell County, Kentucky has been decreasing at an average rate of about 0.3% per year. So your rate is that 0.3%. Take 0.3 divided by 100. So you're going to get 0.003. In 2000, the population started at 88,647. So that'd be your initial amount. And then what they want you to do is figure out your equation and then see how many people should be living there in 2010. So from 2000 to 2010, that would be a difference of 10 years. So plugging it into our equation, we would have 88,647, 1 minus our interest rate, 0.003, and all that's raised to the 10th power. And so after 10 years, if we do this calculation, we're estimating that 86,023 people would still be living there.